All right, everybody, it's time to get our LuBNU haBiBi on. And what we have here is part 4, question number 1, test 2, fall 21. And we have benzene sulfonic acid is the catalyst. It behaves exactly the same as H2S. Oh, yeah, maybe you didn't know that. HOTS is HOSOO with a phenyl and a methyl. And that's this one. And the one above is HOS. And you know what? You don't need any of this. I'll draw the phenyl. It's very similar to HOTS, isn't it? But you just need the short form that's shown up there. You don't need anything. It's a strong acid. Did you get that message? I hope that it's the strong acid. Because HOTS is one of our 7 strong acids. If you don't know that yet, look at some old practice tests where I ask you to draw HOTS. So if you don't know now what HOTS stands for, then you certainly can't draw it either. And it does show up randomly. And I need to do what for the mechanism? Either mechanism that we start with on Monday. Use which pair of electrons? Pi attacks which acid? The stronger one or the weaker one? Which H strong? Yeah. Do not attack the H on water. You will get less than half credit on this question. You'll probably get close to no credit because you're living in an alternate reality and we can't condone such things. All right, so you generate how many cations? Always 2. You got 2 carbons in an alkene, you're going to generate 2 carbocations. In this case, not in equal amounts at all, right? This would not be close to 50-50. We're finally going to get to use the big H word in our explanation. The big H word. No. Okay. We'll address it when we see it. Okay, circle. We're not circling. We're finishing the mechanism. Who remembers the next step? Yep. Oh, you can write down what you made. You can solve and say, when I made that cation, I also made O minus SO2F. Similar story when I made that cation. I also made an O minus SO2F. Now we got to figure out how the O gets onto the carbocation. Where does it come from? With the arrow. Yeah, but what molecule does it come from? Somebody said it. I heard it. Water. They said water. Yeah. We'll put water in purple. This. Lone pair on water. Attacks. Lone pair on water. Attacks. Oh, I got to make a comment. You hand in your activities, you get a point. That's the way it goes. But I've been looking at them too, not taking points off. A lot of you have left lone pairs off when you need a lone pair to make a bond. You will be losing a quarter point every time. I know it's not a lot, but it's going to annoy you seeing all that red on your test. If you make a bond that starts with a lone pair, I got to see the lone pair.
Professor, you haven't practiced it. I missed these just because I think they're there.
In your brain, they're there. I see where it's coming from. Okay, so yeah, but if you're using a lone pair in a mechanism, you better show me the lone pair. All right, and what we have here is O on the tertiary. Still has 2 H's. And looks like I created a bit of a monster situation here with my spatial difficulties. There we go. And we got a purple down here. We are close. This looks like it's going upstairs to that guy. And this one's gonna go to that guy. And in both cases, what's the thing that's happening? This thing had an O with one H, has an O with one H. This thing used to have an O. Oh, it's this one. Sorry. Two H's.
The lone pair from
Yes.
O over there.
The lone pair over here. Yeah. Attacking the H. One, it's reacting with the strong acids H. Yes, and oxonium is a strong acid. That's why we can take the H off now. We can take the H off now, but we couldn't take the H off water before because it had a pK of 16 before, and you don't have any strong bases in this mechanism, right? You will not be taking the H off water in this mechanism. Some of you will try because you see you get to the final answer in half the time. Say, wow, take the H off water from the beginning and I'm done after the first next step. Yay! Yeah, in your reality, hydroxide and sulfuric acid can coexist. In the real reality, hydroxide and sulfuric acid do not coexist. I cannot see hydroxide on this mechanism as soon as I saw this being present. Hydroxide is now haram. You cannot have haram, so you can't have hydroxide in any reaction where a strong acid is present. Okay? All righty. Oh, we're not done yet. This thing needs to become that thing. You see it? Lone pair here goes to that H there. Yes, I'm glad you caught that because I kind of thought I was done too. There you go. And we're not anywhere near done. We have explaining to do, right?
Yeah.
When you do your explaining, you got to do your explaining right beside the carbocation. Please don't tell me one of those products is more stable than the other. You want to know the red that shows up on your test as soon as you try to do that? Not true. -3. Okay? It's nothing about the stability of the product. The rate determining step was forming carbocations. Dead slow. You need to talk to me about which of those two cation formations was just a little slow, quicker. They're both slow. Which one's just a little faster? And it's this one. This carbocation forms faster. This, I don't want to use an arrow.
Oh, we have to write what forms faster?
Well, this is my explanation for C or B.
And then the explanation just doing like LuBNU?
Explain, use it all and react. There's no explanation? Yeah, B, it's B. No, I haven't done any LuBNU haBiBi. This is B. Because this tertiary C plus has more, here's the big H word, I want to hear it. Yeah, I heard it. Hyperconjugation. It forms faster. And just to be clear, this one's tertiary, this one's secondary. So I need you to compare the carbocations, tell me which one's best, and tell me that forms faster. And now we're going to do our lovely labeling. Starting off with our attacker, because every attacker is a LuBNU, right? So hot pink for our labels. Is it attacking a proton? Yes, it's also a haBiBi. The other one's the ELABA. The thing it's attacking is the ELABA. If there's protons involved, I need 3 labels. If there's no protons involved, I need 2 labels. Like the next one. The attacker, you always start with the attacker and go LuBNU. Not attacking a proton. Do not add the BB. ELA gets attacked. LuBNU. ELA. LuBNU. But it's attacking a proton. BB. ELABA gets attacked. I like always starting with the attacker, it's just a good system. Yeah, it's attacking a proton.
Oh,
Yeah, it's a big red area. You get dizzy following it. There we go. Think we got them all? There's one more. She's saying there's one more. Where's the one more? Over here? Just going to here? Yeah, labels on this one, and it's reacting species, that one. Those two, go to that.
Yeah, we got everything.
I think we got it. This thing's getting attacked. This thing's the attacker. That gives everything going there. And we got a nice explanation. Big picture. Got to get small to get big. Okay.
So if we have lone pairs that are not affecting anything, it means we have like something, right?
If you have lone pairs not attacking something, well, they could just be hanging around. Well, you can put all the lone pairs if you want. You're never going to be punished for a lone pair that's really there. Like I could put 3 lone pairs. I could put a lone pair here if you want. Doesn't hurt. That's the only way that is a cation, by the way. But I don't need to see it because you're not using it. I could put all the lone pairs here. That's the only way to get an O-. But I don't need to see the ones you're not using. Oh, I got rid of something. Ilaba. Oof. Okay, and I think we're done.
I have one last question.
About this or moving on? Okay.